Okay, let's get started. The first thing that we want to do is to check your attendance. How can I? Okay. Okay. 명노현.
네,
Okay. 문태혁.
네.
박경준.
네,
박재욱.
네.
박정수.
네.
박현정.
네,
서창현.
네.
오은비.
네,
이규호. 이기석.
네,
이수인.
네,
이신우.
네,
이어진.
네.
이충국. 전성민.
네,
정인회.
네.
정혜민. 네. 조영주.
네,
최민준.
네,
한재호.
예,
함찬종.
네.
홍희정.
네,
황재민.
네.
루이스.
Yes.
Okay. Where is this? Okay. Perhaps. So most of you, I sent out this message to all of you, and I have this Google spreadsheet that explains the plan of this entire semester. And I was hoping that this is explainable. So we had several cases where we had to run this class with a recorded copy because sometimes I was sick on September 14, 16, and from October 19, 21, I'll be traveling to Spain to fix the telescope that I have been working on. And current proposed date for your midterm is October 26th. The idea is that we do this during the class time, meaning from 2 o'clock to 3:15 p.m. And I am thinking now that we run this midterm offline. So you come to the school. We are only with slightly more than 20 people. So we reserve, I guess, 2 large rooms and separate you guys with proper social distance. Then you take an exam. And I hope that's okay to all of you, assuming all of you are nearby to university and so on. So I am going to explicitly write this proposal to all of you to see if you are okay. And then you can see that we have various lectures all the way to 30 classes. This is the requirement from the university, and it's a busy semester. And currently, December 16 is the date for the final, but that can be changed. But that's essentially, this is current proposed plan. Yes, that's what I wanted to say. And then now I am going to start the class. You have any question on the exam, midterm exam? No? Okay. So let's get started. So from today, we are now about to discuss the various scenarios of our universes. So it's chapter 5 is the longest chapter in this semester, and I hope the most interesting part of the this class. So it's a core of the class. At least that's how I think it. So the chapter is, the name is called the Model Universes. So we now discuss various scenarios of our universe, and we start with the Friedmann equation. A pi g over 3c squared. Then I have energy density, which is normally a function of time, and I have curvature term, speed of light. So we've written this equation so many times. This is the evolution of the universe, so scale. And this term is energy density because of this. So energy density. The last part is how the universe is curved. So it's about the geometry. And on top of that, we have what's called the fluid equation, which is relating the energy density with a scale factor. I have one epsilon energy density plus pressure is 0. And for us, when we deal with cosmology, things are very simple in such a way that I can relate the pressure and energy density with a simple dimensionless constant, omega. So now we have all the tools that we need to attack the problem of the evolution of the universe. So let's play with this. First of all, that's 5.1. It's evolution of energy density. So far from our discussion, we know that there are several different types of energy densities in our universe, non-relativistic. We also have radiation. We have something called dark energy and so on. So we want to parameterize the total energy density in terms of individual ones and just sum over all the available kinds will give us the total energy density. And accordingly, motivated by this relation, the total pressure is also sum of different dimension is constant times different energy density part. And also, if we do it this way, this equation is also fluid equation is also satisfied for different species in the universe, but there is only one scale factor. So epsilon I plus omega I is equal to 0. Now let's pay attention to this. Epsilon dot is d epsilon over dt. So I can rewrite d epsilon and remove dt, and I have epsilon. I also have here dt, so I can cancel that dt, and this is becoming minus of epsilon for particular species plus omega I epsilon dA over A. I can integrate this. On the left hand side, I integrate over energy density. On the right hand side, I integrate over the scale factor. And this term gives me log. So log epsilon is equal to log A power of minus epsilon plus omega epsilon. And then we exponentiate each term. So we end up with energy density at certain scale factor should be exponential, not exponential, A power of minus epsilon I. Let's take out that 1 plus omega I. Let's see. I am forgetting factor 3 here, 3 here, 3 here. So I have factor 3 minus. All right. Is it? No. So I divide everything by epsilon I. So once I did that, I don't have this. Just 1 plus omega, and so I don't have this. And when A is equal to 1, which is today, we have to have epsilon I comma 0. So that gives you the constraint or initial condition, boundary condition of the energy density. So this is the basic equation that we derived. And we want to remember this. For non-relativistic matter, omega I, let's say omega matter, L was 0. So if we put 0 here, epsilon over matter at certain scale factor is epsilon matter today divided by A3. And that makes sense because for ordinary matter, if you increase the volume, that's a power of cubic, then your energy density should be reduced by the scale factor power of 3. So that's okay. So that's that. But on the other hand, for relativistic particles or radiation, we argued that omega for radiation was plus 1/3. So if we put that back in here, so I have 1 plus 1/3, that gives me 4/3, so a power of 4. So epsilon radiation at certain scale factor is epsilon radiation today over a power of 4. I briefly mentioned that you need to, there's one extra degree of freedom that allows you to have this sort of dependence on the scale factor for the radiation. You can see that Einstein told me that for a single photon, the energy is related with something like this. As the wavelength, when our universe expands, the scale wavelength is also stretched out together. So that's the energy itself is inversely proportional to the scale, and that this gives you extra term over there. All right. Now let's consider this this one, and let's ask ourselves, for non-relativistic matter, well, it seems to be okay, but for photons, there's a picture, figure 5.1, where when universe is was small, I have photon like this, and when they are expanded, and wavelength is also expanded accordingly, so that we can explain this. But one question that you may ask yourself is, in fact, in the universe, CMB is not the only photons that you can see. Photons are continuously created by sun. There are a lot of stars in our universe. So what's happening to such sources? And also photon dies when photon is absorbed in a surface of matter. Photon dies there. So is this naive argument is okay to describe the universe or not? The answer is yes, and we'll work on some numbers to verify that assumption. So let's erase this part. We can prove that approximately sun, there are 10 to the 45 approximately photons emitted per second. That's a lot of them. So dependence of A-4 for the energy density of the radiation. Is it true? What we know is for CMB, the temperature of CMB today is 2.7255 approximately Kelvin. So if we are interested in CMB today, the energy density due to CMB as of today, this is exactly calculable we've discussed this in chapter 2. This is completely from quantum mechanics of the photon statistics, Planck law or something. So it turns out that this is numerically 4.2 times 10 to the minus 14 joule per meter cubic, or in terms of the unit in particle physics, this is 0.206 606 MeV cubic minus cubic meter. So we can also calculate in terms of density parameter that we defined, CMB 0, which is basically no dividing this normalized by divided by critical density as of today. That's this number. Same unit, MEV turns out to be 5.35 10 minus 5. So number one thing to know is the fraction of cosmic microwave background today with respect to the critical density of the universe today is tiny, 10 to the minus 5. But that's not what we are trying to do here. What we are trying to do is we want to have a rough calculation, rough estimation of radiation density due to stars like suns, how much that value would be compared with this number. So if you take a look at the galaxies, we know that the sort of approximate luminosity density, let's call that to be psi, as star luminosity density. It turns out, this is from observation, it's 1.7 times 10 to the 8 times solar luminosity per megaparsec minus cubic. So if you have a 1 megaparsec, 1 megaparsec, 1 megaparsec cubic in our universe, the average luminosity in the space is this. Seems to be big, but it's tiny if you change this unit in terms of SI unit. That's minus 3 watts per meter minus 3. So luminosity is power per volume. So that's why we have this dimension. Now, let's consider characteristic time of our universe. So amount of time that stars emitting this amount of photons. So that's approximately Hubble time. And this is, roughly speaking, the age of our universe, 13 billion years ago and so on. And if you write in terms of second, that's a crazy number, 4.5, 10 to the 17 second. So what we are trying to do is we want to calculate energy density of starlight. As of today, that's roughly speaking, this luminosity times the amount of time that this luminosity, this part is generating photons. So that's that. It turns out, numerically, I'll skip the calculation, 0.006. So 0.006 MeV per meter cubic. So you compare this number and let's say this number. So the message here is, if you take a look at the universe as a whole, the energy density of the CMB dominates over the photon energy density from the stars. So we don't have to worry about that too much. That's a rough argument. The next topic is, I'm speaking a lot, so I'm thirsty. The next topic is neutrino. If you're not familiar with particle physics, then you don't know what it is. But we have in one of the elementary particles, it's called the neutrino. Its mass is very tiny, but not exactly zero. That's a mystery. But anyhow, this is considered as relativistic particle. So it behaves almost like photons, at least in early universe. So we can also think about cosmic instead of microwave, cosmic neutrino background. People call cosmic neutrino background or cosmic neutrino background. But neutrino is related with weak interaction only. Weak interaction is weak. So, and photon is related with electromagnetic interaction, which is stronger than weaker interaction, of course. So we can also think about temperature of cosmic neutrino background today is fuller or smaller than this number because neutrino was decoupled earlier than photon decoupling because the interaction is weak by definition. So it's about 1.95 Kelvin, and we cannot derive this number because we need a particle physics knowledge. But let's take it as is. Now we want to now say that the energy density of the neutrino. And we want to relate that with the energy density of CMB. And there's a numerical factor. And the numerical factor is 7/8 and 4/11. 4/3. So I'll spend like 5 minutes to discuss where this factor comes from. This is an important piece of information. So I'd like, instead of skipping it, there's some mathematics involved in, but not too much. But nonetheless, I'd like to sketch where these funny looking factors came in. To describe, we need some information about statistical physics. For particle density, we normally call F, which is a function of momentum, is described by the following distribution. You must have heard Fermi-Dirac distribution or the Fermi-Dirac statistics or Bose-Einstein statistics. That's about it. So we define this to be 1 over exponential energy over kT plus minus 1. So we take minus, as we saw in the chapter 4, this is Bose-Einstein distribution by photons and so on. If we take plus, then it's taking Fermi-Dirac distribution, such as electron, positron, and so on. Spin half-integer particles. And what are we going to do with this? In theory, if you are interested in energy density of any particles, all you have to do is to integrate over, for energy density, you need the energy, and this particle density function, and integrate over all the possible momentum phase space, and then you need to have a factor here, 2 pi cubic h bar cubic, I think, h bar 3, h or h bar, cubic, and you have factor g here. This factor g is what did I write? Additional degeneracy. Such as spin and so on. So in principle, we can calculate this for photons and so on. So let's discuss about it. So for that, let's remove only half of this. Today I need to take timing carefully because I have another meeting at 3:20. So I'll have to finish on time today. Now normally this is a triple integral. So we want to change d3p in terms of energy for relativist particle where you can neglect the mass. So this is 4 pi p squared dp, and you change it to energy. So I have 4 pi e squared c1 to 3 de, because p is equal to e over c for relativistic particles. You plug at it, then your triple integral becomes one-dimensional integral, and it will turn out to be epsilon s, and the factor will be different because you have extra stuff, g 2 pi, well, 1 over h plus c power of 3 integral. Now I integrate over 0 to infinity. I have e. I have 2 of them. I have another one. So e power of 3 and exponential e over kt plus minus 1 de. Now the problem is this integral. You can do this is essentially changed to this u3 exponential u plus minus 1 du. Basically, what I'm going to do is to define k e over kt to be u. Then this is essentially this. This one is either pi 4 over 15 this is for fermion. This is, I'm sorry, this is for boson, right? This is for boson, this is for fermion. And for the fermion, you have an extra term, 7 over 8. So essentially, this funny looking term is from there. Now we want to attack this second part. And to discuss the second part, you need the concept of the entropy. So the entropy density is a function of g t power of 3. So entropy density is proportional to the internal degeneracy, such as spin times temperature power of 3. If you say you don't know where this is from, sorry, this is from statistical mechanics. Awesome. This is fourth year undergraduate level of physics. That if you don't know, you have to take a look at your textbook, statistical physics textbook, and look for the entropy density in terms of temperature. So that's that. So we can define two temperature scale, T mu and T, what did I say? T mu and T gamma. So T mu is when neutrino is around So we have neutrino is scattering with E plus E minus, and we also have photon. But when T gamma, and the universe is cooled down so that neutrino is decoupled. So I only have photons, and these electron and positrons either annihilate or they go to atom, neutral atom. So if we do it, and we want to write, okay, if I have G for gamma and temperature of gamma power of 3, we want to say is that since the universe is as a whole, the entropy density should remain constant. So we want to say G, let's say gamma E plus E minus T mu power 3. So I am taking a ratio of T neutrino over T gamma, and from this equation, I have give you here. Then I have G gamma in the numerator. I have G gamma E plus E minus, and I have 1/3. Photon, can you see me? Photon has spin up, spin 1, so it has spin 1 up or down. So it's vector 2. Here I have photon 2 plus. Now I have a fermion, and the fermion, I have this vector. So I have vector 7/8. And electron or positron also have spin 1/2. So it has only also 2 degeneracies, vector 2. So this is for electron, and I have positron. So vector 2, 2, 2 cancelled. And this is 7/4. So I have 1 plus 7/4. So that's 11/4, and it's the denominator, so I flip it. So this is becoming 4/11, 1/3. So we are getting there. I'm going to use this part. So original question, epsilon, I have epsilon CMB. I want to compare with this. This is originally, I have from neutrino to CMB, I already have 7/8 because one is fermion and the other is boson. And where did I erase? The energy density has the dependency on the temperature power of 4. So we have T mu over T, let's say gamma, power of 4. So that brings me 7/8, and this is T mu over 8. This guy power of 4, so 4/11, 4/3 ECMB. And that's essentially this. Numerically, I'm sorry for busy. Numerically, this is what? Points. So in terms of omega, normalized mu, I didn't say explicitly that this is per one neutrino, one flavor of neutrino, one neutrino, and we have 3 flavors. So in the case of total neutrino density normalized by critical density, we need a factor 3. And then 7/8, 4/11, 4/3, omega CMB. And this numerical factor 0.681. So the neutrino energy density in total, when we have 3 different families of neutrino, muon neutrino, electron neutrino, muon neutrino, and tau neutrino, we need factor 3. That brings us about 70% of CMB energy density turns out to be the neutrino density. So you cannot ignore energy density from neutrino. So that's the conclusion so far. We have a homework there. And let's move on. I'm gonna erase this one more time. For the record, I want to take shortly I just take a picture of this. And then let's erase. What time is it? 47. What do we want to discuss from now on? So numerically, we are interested in total radiation as of today. And we know that that's coming from CMB plus neutrino part CNB or C neutrino B. This is approximately 9 times 10 to the minus 5. Still very small. And we know that there's 2 more different components of the energy density in our universe. This one, I put 0, 0. That means we are sure about this numerical value down to 2 digits. But energy density of dark matter, energy density of dark energy, we don't know quite well. But we have rough feeling that normal non-relativistic matter, the normalized density. So this is including ordinary matter like us, Earth, Sun, etc., as well as dark matter, is known to be around 0.31. And the corresponding dark energy density is 0.69. 0.31 plus 0.69 is 1.0. So there's actually no room for radiation. So that's why it's very small. And normally observation tells us that our universe is fairly flat. We cannot say for sure it's dead flat because of the uncertainty in the observation. But we can assume spatially by a flat. So this picture of radiation is this amount, ordinary non-relativistic matter, this amount, dark energy this amount and our universe is flat, it's a sort of reference picture of our current universe. So it has a particular name. This thing is called a benchmark. Model. So from now on, when we discuss benchmark model, I refer these components with our universe being flat. So we'll use this term benchmark model later on frequently enough so that you won't be able to forget. In this benchmark model, if I'm interested in the ratio of energy density due to dark energy divided by ordinary matter today, it's nothing but the ratio of this. 0.69 over 0.31. So about factor 2. 0.23. But we know if I'm interested in dark energy at certain scale factor over non-relativistic matter, this is epsilon lambda 0 because dark energy, there's no dependence on the scale factor. But for ordinary matter, you have matter today and should be scaling a power of 3. So you can divide everything by critical density so that I can also rewrite omega lambda 0 divided by omega m0 a minus 3. Should also be satisfied. Yes. So there was a period in the past the energy density of dark energy was equal to the energy density of ordinary matter. So E lambda at particular a scale factor, let's call that to be lambda m, is equal to epsilon m at a lambda m. So this term will be identity. So a lambda m should be equal to omega m0 over omega lambda 0 power of 1 over 3. From benchmark model, we have this. This turns out to be 0.766. So today, scale factor is 1. So when scale factor was 77% smaller than today's value, at the moment, the energy density from dark energy and ordinary matter were equal to each other. Then what about 두루두루두루. Radiation. This is 0. For here I have a power of -3. Here I have a power of -4. So I have overall factor A. So at radiation was equal to matter component of non-relativistic energy density. This should be 1, so A should be equal to E normalized by critical density. So that's the ratio of this to that. So when radiation energy density was equal to non-energy density of non-relativistic particle, that was much earlier than the time when dark energy density was equal to energy density of the ordinary matter. So you remember that I was drawing something like this. This is A, and this is energy. So energy density was initially, it's steeply falling because the radiation dominated, and that was a power of -4. And in some point, you face a, this is, let's call that to be radiation matter. So radiation and matter. In some point, you reach to this point, and then the steepness is slowing down. Because this is a minus power 4, this is a minus power 3. And almost today, you have a lambda m. And then the energy density is essentially flat. Of course, this is a continuous process. There is no boundary, but this is sort of qualitative description of what has happened to the history of our energy density. Okay, we have about 15 minutes to go. So let's now turn our discussion into case by case. We discussed particular case of a universe. We start with the empty universe. We also discussed the universe with only matter, only radiation, only dark energy, and so on. So let's use the other side, where I think things are much nicer. Hopefully it's okay. Next topic, 5.2, empty universes. First of all, let's rewrite the Friedman equation, a square. And remember, suppose we have various components. And we used to have a square in the denominator, so we are multiplying a square everywhere. So now I have a, instead of -3, I have -1. And then curvature term. So that's the Friedman equation to play with in the beginning. And I should have written this first. So for empty universe, what do I mean by that? I don't have any energy density. So it turns out that a dot square is only curvature. That's the Friedman equation. One solution, kappa is 0. Then a dot is 0. What this is? This is on empty static and flat universe. Very boring universe. It's empty because epsilon is 0. Static because nothing moves around. Flat because kappa is 0. But nonetheless, this is one possible solution of empty universes. Now, let's say, okay, I can assume kappa is equal to -1. Kappa is equal to +1 is forbidden. Why forbidden? A is a scale factor. It's a physical quantity. So it has to be a real number. So kappa is -1. Therefore, A dot is equal to plus minus C over I0. Now we further consider, okay, A dot should be greater than 0. It's just choosing one sign. What does it mean? Well, it's expanding universe. And a dot is a constant. So A should be proportional to time. And we have this always this boundary condition. So T0 should be from this inverse. So it's R0 over C as the definition. So our universe, empty universe, has the scale factor just linearly increasing as a function of time. If I am interested in H0, which is by definition is A dot over A evaluated at today. A dot is we chose to have plus with C over R, and A at T0 is equal to 1. This is T0 of inverse. R0, yes. So we want to write H0 over T minus, I'll explain why we want to do this in a minute. So H0 is this, so I have T over T0 minus T minus 1, because T0 is cancelled. And this is nothing but A. So my A is H0 T minus T0 plus 1. Why we did that? Well, because I want to, well, someone already did, not me. Someone wanted to make a plot of H0 T minus T0 and the scale factor. It's just one way of parameterizing dependence between time and the scale factor. But time is parameterized in such a way to be, first of all, dimensionless. This is time, this is inverse time, so it's dimensionless as a function of scale. So when here's I can say, okay, that's a 0. When is 0? When t is equal to t0. But whatever a is, the value of a at this point should be 1. And as t goes up, it's just linearly increasing. So I'm going to have something like this for my empty universe. Of course, a dot should be greater than 0. Alpha is minus 1, and so on. And that's, let's say, that's the picture 5.2 is trying to tell you. Here we have many curves, but the red one is sitting there. And as we will discuss, we have other universes, matter dominant universe, radiation dominant universe in green, and lambda dominant universe in dot to dashed curve. We'll come to that, but for now, let's take a look at this red one. So it's a simply a linear relationship. All right, already 3:10, and then okay, I better stop here to make you happy. We have a little earlier ending of a class, or you're not happy. I don't know. Any questions? Everything is clear. Is it? No question? You know, you can always ask a question on KakaoTalk. I should be able to answer if I know the answer. No question. All right, I remind you that we are going to have a midterm exam on October 26th, I think. And then my original default proposal is to have a midterm offline so that we don't have to worry about cheating, not being fair, and if you are a bad person, you can bring I don't know, some genius person who knows this stuff very well on behalf of you to take midterm when I do it in online. So in order to prevent that possibility and to be fair to all of you, I am going to have midterm exam offline as a default. If you have a problem with that, please let me know. I will also send out this message to all of you again. Okay, that's it for today. We will stop here, and thank you for coming. And then I'll see you on Thursday. And if you have a question, ask question on KakaoTalk. Bye. Okay, how do I end this? Stop recording.